Neural network from scratch implementation with Python. That's the topic of this video. And before we go to the actual Python code, we'll spend a little bit of time on understanding the overall flow and architecture of a classic neural network. So here in the neural network, each neuron is connected to other neurons, but not all connections are equal. Instead, each connection has an associated weight that we can see in this image here, W1, W2, W3. So speaking formally, a firing neuron propagates an impulse of 1 to the outgoing neighbors, while a non-firing neuron propagates an impulse of 0. You can think of the weight as indicating how much of the impulses of the firing input neuron indeed, is forwarded to the next neuron via this connection. Mathematically, you multiply the impulse by the weight of the connection to calculate the input for the next neuron. Like what we are showing in this image, x3 here is a weighted sum. X3 is the value in this node here, is a weighted sum of the input value and the weights of the corresponding input neurons. So we can say that input vectors are fed to the neurons with weights assigned to represent importance. That's what weight is all about, that they represent importance. Calculations performed within the neuron are weighted sum and activation function. So for example, this is a neuron, this is a node, and the calculation performed within it has these two aspects. One is a weighted sum and one is an activation function. And all the weights are coming to this neuron from these input neurons. Let's quickly check weighted sum function in the context of neural network. It is also known as linear combination. The weighted sum function is the sum of all inputs multiplied by their weights and then added to a bias term. This function produces a straight line represented in the following equation. That is, Z is a weighted sum, x1 w1, x2 w2, x3 w3. That's how we calculate the weighted sum here. And for Python, it will just be an np dot. It's a dot product between the weights and the input values of the input neurons. This is another way to represent it, but this is an activation function. So after the sum of the products of weights and input pairs are calculated, the resultant weighted sum is followed by an additional function, which is called the activation function. And this is what that is being represented here. F is an activation function here. So at a high level, a neural network is a collection of nodes where each node has an adjustable float value, and the nodes are interconnected as a graph of return outputs in a format that is dictated by the architecture of the network. The network constitutes three main parts: the input layer, the hidden layer, and the output layer. Let's quickly go over their definition. Input layer contains a feature vector. Hidden layers, that the neurons are stacked. Hidden layer are layers of neurons, and the neurons here are stacked on top of each other in hidden layers. They're called hidden layer because we don't see or control the input going into these layers or the output. All we do is feed the feature vector to the input layers and see the output coming out of the output layer. And then the weight connection or the edges, for example, all these weights are the edges, that is a connector from x1 to this neuron, x2 to this neuron. So what they are, weights are assigned to each connection between the nodes to reflect the importance of their influence on the final output prediction. In graph network terms, these are called edges connecting the nodes. Yeah, that's right. And the output layer, we get the answer or prediction from our model from the output layer. Depending on the setup of the neural network, the final output may be a real valued output, that is a regression in the case of regression problem, or a set of probabilities, or which is the case with classification problem, either binary or multiclass. So this is determined, the output layer is determined by the type of activation function we use in the neurons in the output layer. So for this example, we have this very simple version of a neural network structure. What we have here, the first layer are the two input layers, and then a hidden layer, and then a single output layer. And this is a fully connected neural network. What we mean by that is that I'm connecting each of these nodes to each of the other ones. So both these nodes has three outgoing connection to these, and this, and then also this node has three outgoing connection to this one, and this one. So there is no skip connection. All are fully connected. And similarly here, there's only single connection here because my output has only a single node. And how I'm getting the value of 1, 1.3, and 0.8 here, that's because of the same thing that we just discussed, that weighted sum. So this one is a weighted sum of the values from initial neuron and the weight. So 1 into 0.8 plus this one into 0.2. Similarly, this 1.3, if you cannot see that, let me zoom it a little bit. So if you cannot, yeah, so this 1.3 is coming from weighted sum of 1 into 0.4 and then 1 into 0.9. You can see that this is the value 1, and I have a 0.9 connection here, and also this is the value 1 here, and I have a 0.4 weighted connection to this node. So I just multiply them and sum them. And so now the concept of activation function and how the output from the hidden layer is calculated. So remember, we already discussed this concept of the activation function here. That is, after the sum of the products or the weighted sum is calculated, that is passed through a activation function. So in this image, this f is an activation function, and that activation function takes as its inputs these terms. This term is a weighted sum, and W0 here represent a bias term, but for the sake of simplicity, I have not included the bias term in our discussion till now. But of course, bias term is a very common in every neural network. We'll come to that in a short while, but for now, just note that this f is an activation function, and that takes as an argument or as an input to the function as the weighted sum. So let's see how this comes out in our neural network. So again, this is a hidden layer, and we already received or already calculated this value 1, 1.3, and 0.8 as a weighted sum. But now we have to calculate the output value from this hidden layer, which is 0.73, 0.79, and 0.69. Let's see how they are calculated, and that's where the activation function comes into play. And we have many kinds of activation function, but these are the most common ones, that is sigmoid, ReLU, tanh, and linear activation. So sigmoid, we will use for this example, we will use the sigmoid activation, which is this expression 1 by 1 plus e to the power minus x. And here x represent the weighted sum that we just calculated. That is, this is the function, and it takes as an input to be passed to the function, and that input is minus this x value. So let's see. And this is the graph representing all these functions. So this is the graph for sigmoid function, this is for ReLU, this is for tanh, and this is the linear activation function. Okay. And now we see the calculation. We already received this value of 1, 1.3, and 0.8 here, referring to this this calculation. That is, 1 is a weighted sum of this, and 1.3 is a weighted sum of 0.4 coming here, and 0.9 coming from here, 0.9 coming from here, and 0.8, this value is a weighted sum of 0.3 coming from this node, and 0.5 coming from this node. So you already have this value. Now that value need to be passed through the sigmoid function, and this is our sigmoid function. So I pass 1 as an input to the sigmoid function of this, that is 1 over 1 plus e to the power minus 1, and get this value 0.73. Similarly, I pass 1.3 as an input to the sigmoid function for this node, and 1 by 1 plus e to the power minus 1 3 gives me 0.79, and that's what we see. And so for the third node here, I get a value of 0.69. And then the final output value, that is output node value, y predicted, that is a predicted value of y for us. That's again the weighted sum of these values. So the weights for this connection, that is the first hidden layer, first node of the hidden layer to the output layer, is 0.3. Multiply that by the value of 0.73 that we just calculated here with the sigmoid function. Similarly, do for the second node, that is 0.79 we received from here. Multiply that with the weight for this layer 0.5, and so for the third node 0.69 that we received here, and multiply that by the weight here for this connection, and I finally get a value of 1.235, which is a predicted value at the output layer. And remember once again that these weights actually represent the importance of a connection. So how important this connection is compared to this connection. So obviously we can see, for example, here 0.8 is more than 0.4. That means this connection is definitely more important than this connection. And the whole idea of forward propagation and back propagation in neural network structure is adjusting or fine-tuning these weights, and we'll come to that in a moment. So this 1.235 is the output value from the output layer, and this is the value that needs to be compared with the actual ground truth, that is actual value of y. So this is my y predicted, and that has to be compared with the y actual. And so the loss concept comes here, that how much of my predicted value differs or varies from the actual ground truth or actual value of y. So let's see, for calculating in the neural network, we have mainly two kind of predictions: categorical variable prediction and continuous variable prediction. And accordingly, we have different kind of losses. So when we calculate the continuous variable predictions, we normally apply these MSE, mean squared loss. And here the yi is the actual y, actual value, and yi hat is a predicted value, and this is the formula for MSE. And when we deal with classification problem, either binary classification or multi-class classification, there the loss calculation is different, and we call it cross entropy. And this is a formula for binary cross entropy loss. That is when we are dealing with a binary yes no or 0 1 kind of variable classification problem. And this is the formula for categorical cross entropy loss when there are multi-class problem for categorical variables. A simple way to visualize the cross entropy loss is to look at the prediction matrix, this image here. So here it's a multi-class classification problem that we are dealing with. We have 1 2 3 4 5 different classes: dog, cat, cow, hen, and rat in an image classification problem. And the neural network model of ours is predicting the probability that a particular image is a dog or a cat or cow and so on. And these are those probability or predictions. So for example, here on the first line, 0.8, the model is predicting there's an 88% chance, or the probability is 0.88 that a particular image is dog. And in that case, the cross entropy loss is given as below, given as here minus log of 0.88, and which is 0.128. And similarly, we calculate the probabilities and cross entropy loss for various predictions, and we can see that when the predicted probability is more for the correct class, then the loss is less, which is kind of obvious. So now we have gone through the method of losses, the method of the neural network architecture, and the activation function used. So the next step is the main topic of neural network, which is forward propagation and back propagation. So what we learned till now about loss function and calculating weighted average and passing that weighted average as an input to a function called activation function, all these in essence is a feed forward motion or forward propagation. So what we do in basically is at each neuron in a hidden or output layer, the processing happened in two steps in the forward movement, which is one is pre-activation and the next one is activation. So in the pre-activation, it is a weighted sum of inputs, that is a linear transformation of weights with respect to inputs available. Based on the aggregated sum and activation function, the neuron makes a decision whether to pass this information further or not. And the activation stage, which is after we calculate the weighted sum of inputs, that is passed to the activation function. An activation function is a mathematical function which adds non-linearity to the network, like we used sigmoid function, and there are other like hyperbolic tangent, ReLU, and softmax. So if I have to make the whole feed forward motion in 4 steps, they will be as follows: that perform the sum product at each neuron, then compute the activation, repeat the first 2 steps at each neuron until the output layer, and compute the loss by comparing the prediction with the actual output. So that's in a sense a feed forward motion. So in a nutshell, in the feed forward propagation, we connected the input layer to the hidden layer, which then was connected to the output layer. In the first iteration, we initialized weights randomly and then calculated the loss resulting from those weight values. That was my feed forward propagation. And now the next part, which is back propagation. In back propagation, we take the reverse approach. We start at the loss value obtained in the feed forward propagation at the output layer, last output layer, and update the weights of the network in such a way that the loss value is minimized as much as possible. So back propagation is exactly the opposite movement in the opposite direction. We start at the end at the output layer and update the weights, continue updating the weights going backward so that my final loss is minimized. And so here the full backpropagation works on a principle of calculus called gradient, and we apply a very famous formula of differential calculus called chain rule to calculate the gradient of all these layers. And I have a separate video on exactly how chain rule is implemented and why chain rule is important, and I'll give the description of that in this link to the description of this video. So for now, let's go over quickly on the very basic algorithm of the back propagation, which is there are mainly 3 steps: change each weight within the neural network by a small amount, one at a time, then measure the change in loss when the weight value is changed. That is, we change the weights and then measure the loss, and then update the weight by this factor, that is k minus k and then del L by del W, where k is a positive value and is a hyperparameter known as learning rate, and del L and del W are the change in loss and change in weight respectively. Note a particular point here that the update made to a particular weight is proportional to the amount of loss that is reduced by changing it by a small amount. So intuitively, it makes sense, because if changing a weight reduces the loss by a large value, then we can update the weight by a large amount. However, if the loss reduction is small by changing the weight, then we update only by a small amount. And if all these steps, that is a feed forward propagation and back propagation, is done once, that's called one epoch. And in a typical neural network, the number of epochs can range from 10, 20, 50, and so on. And also, a neural network contains millions or sometimes even billions of weights and nodes. So calculating this gradient, this value del L by del W is not always optimal for each and every node, for each and every weight. So we make use of a very handy calculus technique named stochastic gradient descent and chain rule. I have a separate video on that for the back propagation. I will give a link to that video in the description. So for now, let's go over to the main steps of the whole process. Yeah, so this is the overall steps. In the forward propagation stage, the data flows through the network to get the outputs. The loss function is used to calculate the total error. Then we use backward propagation algorithm to calculate the gradient of the loss function with respect to each weight and bias. Finally, we use gradient descent to update the weights and biases at each layer. We repeat above steps to minimize the total error of the neural network. So now I will pretty much start with a very simple and manual kind of Python implementation for the for our neural network for this architecture. That is, I have one input layer, one hidden layer, and one output layer. And this will not involve exactly all the stochastic gradient descent or chain rule formulas. This Python implementation is just to show at the basic level how a neural network is implemented in code. Later in a separate video, I will go through the exact from scratch implementation of neural network. Okay, so let's jump to the code. So here I am in my VS Code. So first, revisit that the actual algorithm of the whole neural network. I am just copy pasting from my earlier notes and presentation. 1 second. Okay, the high level strategy is as follows. We perform a sum product at each neuron, compute the activation, repeat these first two steps at each neuron until the output layer, and at last compute the loss by comparing the prediction with the actual output. So first I am going to build a forward propagation function. It is going to be a function that takes in input data, current neural network weights, and output data as the input parameters or arguments to the function, and returns me the loss of the current network state. This function will also have a bias term associated, but I think this just for this function I do not need to worry about the bias terms. When I initialize the weights, that weight matrix will have its bias terms. So forward weights. So first I'm going to calculate the hidden layer values by performing a matrix multiplication, that is np dot numpy dot function. But remember that we calculated the values at each neuron with the weighted sum of inputs and weight values. That's how I connect my input and the input layer with the hidden layer. So and we called it the pre-activation stage, that is before invoking the activation function. I have to calculate these weighted sums, and after these weighted sums are calculated, then I will feed that to the activation function. So I will just rename a variable, long variable name, sorry for that, just to be super clear here. Pre-activation hidden layer value equal to input np.dots of my inputs and outputs. Sorry, that's not the output, that's the weights. And I will use weight 0 here because the weight variable will be a full 2 by 2 matrix, or I think that would be, I will initialize the weights at a 4 by 1 matrix. I will detail the weights in a bit. So for now, just remember this weight 0 is my coming from my input layer number 1, and I will also have the bias term, which I will add, that would be W on weights 1. I think it's better if I initialize a weight so that I can be very clear about you can be very clear about the structure of the weights and what they are. So just give me 2 seconds to do that first. Now, before we structure our weight matrix, let's have a quick look in the neural network architecture that we are using for this example. This is the input layer, this is the hidden layer, and this is the output layer. And we need a total 4 list of parameters within our neural network. 2 lists for the weight and bias parameters that connect the input layer to the hidden layer, and another 2 lists for the weight and bias parameters that connect the hidden layer to the output layer. And as I can see that we need this hidden layer will have an output for each of these node. So we need a list to have these outputs as a element of the list, and also the final output layer will have a single value as its output. So now let's get to the structure of our matrix for the weight. And here is my weights matrix. I have generated these numbers with randomly, and included all these np.array numbers inside a matrix. That is, the full thing is a matrix, and we can quickly print this matrix. Print 1 second. So let's print it in a list format. Print w for w in WS. Okay, let's run it. What happened? Yeah, it printed the third time. I don't know why. All right, so this is our weight. So the first, this is w0 is this value, the first 2 list, and then w1 is this, the second one, and this is my w2, and this is w3. Let's print it out, and let's so that we can see properly. Move panel to right. Okay. Print w. Tired of this auto intelligence from VS Code. On w0. Okay. Is it printing? Weights 0. Again, it printed the 4th time. My VS Code sometimes acts crazy. All right, that's weight 0. Let's do this thing for weight 1, 2, 3. Okay, I printed all of them. Yeah, so weight 0 is my, this is my, is a weight 0 is the input layer, is a weights for connecting the input layer with the hidden layer. Input to hidden layer connections. And then this is the bias term for bias terms from for input to hidden layers, and this is also, and weights 2. Now I am in the first output layer that would have three values. That is the hidden layer, first output layer after the activation function. So these are those three values. First, so this is my first output layer, and weights 3 are my final output layer value. Final output layer. Final means it's the second output layer, second layer. That is, for our case, it is final. Okay. So this is the structure of the weights. So in the feed forward, we need both weight 0 and weights 1 in the feed forward function that we were almost started writing. So because feed forward function is actually calculating the weighted sum between the input layer and the first hidden layer. So, and what are those weighted sums? They are the the dot product of weights and bias terms. So let's do that, carry on with that. One second. Okay, so here, okay, I was just losing a track. Now I have already calculated the pre-activation hidden value, and now I am going to apply the sigmoid activation function on top of the hidden layer values obtained in these previous steps. That is a pre-activation hidden layer. Invoke my sigmoid. Remember, for this example, we decided to use sigmoid as an activation function. Hidden value activation equal to 1 by 1 plus, I'll be using numpy as exp function dot exp, and that would have the minus value, the negative value of this my weighted sum, pre-activation hidden layer value, right? Why I'm not getting? Oh, I have not imported the all the packages. Let's import them. I also need a package called deep copy, because in the next function I will be playing around with the weights, so I don't want to modify the original weight. So again and again I have to create a deep copy of the weights. So copy. For the final plotting, we need matplotlib. SPLT. Okay. All right. That's all the packages we need. Okay, so I'm done with the hidden value post activation. Now I am only left with the actual calculation of the output value and then the mean squared error. Output value. That would be my weighted sum again. Let's call it, I don't know, output value. Equal to hidden value post activation, and I am calculating the, I need the weights matrix again. First output layers and the final second output layer. So I need these two terms for here. Hidden post activation. Weights 2 and weights 3. Okay, output value, yeah. And MSE, that is a mean squared error, is easy. That is just the formula ID mean squared error. What's the spelling of squared? I don't know. SQUA. Yeah, that should be it. I don't know. I mean, squared error is np dot mean. I need to square the error. So np dot sqi, and between my output value and my outputs. The function originally had output, yes, that's the function I need. And from this feedforward function, I only return this mean squared error. Okay. Yeah, so that's my feedforward function, feed propagation function. It takes an input, output, and waits, calculates the pre-activation hidden layer value, invoke the sigmoid, calculates the output value, and ultimately returns me the mean squared error. And remember, our architecture is very simple, so that's why this function is also simple. Oops, I'm sorry, I made a mistake in calculating this output value, that is a dot product between, this will be between hidden value post activation and weights 2 here, and then I have to add the bias term, that is weight 3. Yes, now it makes sense. I think it's better to quickly rephrase these definition of various vectors within the weight matrix so that it becomes clear. So weight 0, this is the weight values connecting the input layer to the hidden layer. So these are weight values connecting input layers to hidden layers. And weight 1, this is the bias terms associated with the hidden layers nodes. Bias term associated with the hidden layers node. Remember, we have 3 hidden layers node, so we need 3 values under weights 1, and that's what we have. These vector here, this vector, and weights 2 is the weights connecting the hidden layer to the output layer. And because we have 3 nodes in the hidden layer, so we need 3 elements under weight 2 vector. So let's rephrase it. That will be weights connecting the hidden layer to the output layer. Okay. And the final one was final is, this is a bias associated with the final output layer. So this is the bias associated with the final or the second final output layer. I think just better to delete the second output layer value. Yeah, now it is much more clear. So now for these output value the calculation, we need the weighted sum of the hidden value post activation and the final output layer. So that's what we are doing here now. Np dot product between the hidden value post activation and the vector of weight 2, and to that I'm adding the bias term of the final output layer. Yes, this makes sense. Now, for understanding it properly, let's keep the code and our neural network side by side. So this is our neural network input layer here, then the hidden layer and the output layer. So this pre-activation hidden layer value, this variable, I am calculating the weighted sum with np dot dot. These are these values here. So just like here it is explained with h11 being the pre-activation hidden layer value for the first node, h12 is for the hidden pre-activation hidden layer value for the second node, and h13 is a pre-activation hidden layer value for the third node. And this is just the weighted sum of the weights and the initial input value. So that's this line. Np dot dot input and weight 0. Weight 0 vector is my weights, and weight 1 is a bias term. But remember that in the image, for the sake of simplicity, we did not keep an image of the bias term, but in actual code implementation we have a vector for bias term as well. So these h11, h12, h13 are calculated by this line of code, and this is called pre-activation hidden layer value. And now the next line of code is invoking the sigmoid function, and that will calculate the hidden value post activation. So let's go to our sigmoid function calculation. Yes, so sigmoid function will take as its input these pre-activation hidden layer value, and that's what this is doing. That this function pre-activation value was 1 for this node, and that is taken in this sigmoid function, and that gives me the result of 0.73. And that's exactly what is being implemented in this line of code, invoke sigmoid. That hidden value post activation value is 0.73 for the first node, and that is being arrived at by invoking the sigmoid function and passing into the sigmoid function our previously calculated pre-activation value. And now finally the output value in the image, that is this value at the output layer. So that is again the weighted sum of these weights, 3 weights and 3 post-activation values. So I am getting 0.73 multiplied by 0.3. That is these weights multiplied by these 0.73 value, then this weight multiplied by 0.79, and this weight multiplied by 0.69. And that's what is being achieved by this line of code here. Output value is an np dot product between the hidden value post activation vector and the weight 2 vector. And remember what was our weight 2? Weight 2 was the weight connection, the weights connection between the hidden layer to the output layer. Weights connect, yeah, I think I'm just rephrasing it. Weights connecting the hidden layer to the output layer. So this weights 2 vector is these vector, and these vector are all these values. That is 3 weights and 3 vectors. Okay. Yes. So that's my output value. In the image, I got it 1.235, and this 1.235 is a predicted output value from the output layer, and that needs to be compared with the actual value to get my mean squared error. And that's what I'm doing here in the last line of code in this function. That is that's np.mean, and mean is being taken of the square of output value minus outputs. Output is another, this is the real output, actual outputs. Okay, so that should simplify the relation between the neural network image and the code. And the next we have to actually implement the function for training the weights, that is a gradient gradient calculation, and training and updating the weights. Now I'm going to train the weights with the process of gradient descent. So I'm naming this function just train weights gradient descent, and it will take 4 inputs, 4 arguments, which are the inputs to the network, then the actual output, that is a ground truth, and the weights, and the last one is learning rate, LR. So now first I'm going to create some deep copy of the weights, because at various stages during the training process, I have to manipulate the weights and I have to deal with the weights in various ways. So I do not want to change or alter the original weights. So I'm just creating some deep copy of the weights that has been given in the argument to the function. So let's do weights. Remember, we already imported this library here, deep copy. It will take weights of the. Yep. And now I initially want to get, before the training starts, I have to get the original loss, because that will be my, remember how the network works, that this training, the whole training is actually the back propagation, and the whole back propagation starts from the end and moves to the left through the network. That it starts with the loss from a particular epoch and then moves backward with the gradient descent process, updating the weights so that the loss gets minimized. So first I have to get the loss of a epoch, and that's what I'll do. Original loss equal to, and how do I get the loss? By invoking my forward propagation function, because it returned me the mean squared error. Forward propagation, and it takes inputs, outputs, weights. Weights, I think, yeah, I'll pass weights original. Yes. All right, and now the actual, I have to loop through the layers of layers and just quickly take a look at our network. I think, yes, this is a network, one input layer, one hidden layer, one output layer. And I'm starting the back propagation training. That is my current function that I'm writing currently, that starts here, where the loss is generated after the feed forward. And now I just wrote the code for the feed forward function, and I get the loss, and that loss now need to be the guiding point for updating my weights so that the loss ultimately gets minimized. Okay, original loss, and now for so this function is loop to the network layers. For I layer in, all right, that would be my weights original. and take a quick look at the what was our original weights, because that's a matrix. We created it manually, this matrix. And remember that we discussed already that there are a total of 4 lists in this matrix. 4 lists or 4 arrays. The 2 lists for weights and bias parameter that connect the input to the hidden layer, and another 2 lists for the weight and bias parameter that connect the hidden layer to the input layer. Sorry, the hidden layer to the output layer. So weight 0, this is the weight values connecting the input layer to the hidden layer. Weight 1 is for the bias term associated with the connections between input and the hidden node. Weights 2 is a weight connecting the hidden layer to the output layer, and the bias, the final weight one, that is weight 3, this value here, that's a bias associated with the connection between the hidden layer and final output layer value. So now I have to loop through the weights original, and for so these will loop through weights original I layer. The layer will be each layer, and now again I have to loop through the layer index, and here I have to make use of an numpy function called nd enumerate, which will give me the actual coordinates of each element. And that's because my each layer are of different sizes. Yes, each layer of different sizes, which is reflected in our weights parameter as well. The first list has 1, 2, 3. It's a shape of 3, and the second one also is a single array, and so on. So I have to, yeah, so I have to make use of nd enumerate. Let's see how it turns out. For index WA weights in np dot nd enumerate. Quickly check their definition. Multi-dimensional index iterator returns an iterator yielding pairs of array coordinates and values. So, okay, enumerate, and that will take my layer. Now I'm looking through the layer, and again I am going to store my store a deep copy of original w. Yes, here, where it's temp equal to deep copy weights. Yeah, makes sense. And now the crucial part, I have to update each of the weights. So what I'm doing is I select its index weight, I select the index of the weight, and I add a small value. I will be adding a small value of 0.0001, and because the next loss will be calculated based on this updated weight. We already are given the original weights, and the whole process of backpropagation and the gradient descent is about updating these weights gradually to see how the loss is changing. Updated. Yes. So weights temp, sorry, weights temp, and that would be my this I comes from the outer looping, and now for the inner looping I have to get hold of the index plus equal to 0.0001, and after updating the weights I have to calculate the loss. Calculate new loss after updating weights, which will be, let's define a private variable loss. forward. And again, for the loss calculation, I have to make use of the forward propagation function, and that would take inputs, outputs, and now it will take the updated weights, and that the weight has been already updated. So let's give this here. Okay, and now that my loss is updated, I have to calculate the gradient. So gradient is simply, we calculate the gradient, that is a change in loss value due to the change in weight value. Here the change in loss value is a new loss calculated with updated weights, and the change in weight value is this this number. So just put it in here, loss plus minus change in loss value, the original loss, and divide it by 0.0001. That's my gradient. Note that what I'm doing here above in this line is updating the weight by a small amount and then calculating the gradient, that is change of loss with respect to change in weight. And this is exactly equivalent to the process of differentiation, that is differential calculus, but I'm not making use of any formulas here. Here I'm just doing it very much manually without using the calculus rules. And finally, now that my gradient is calculated, I have to update the weight value. So WGIG, make mistake with the weight spelling each time. It's updated. Did I declare this variable yet? I don't think so. Here, let's declare it here. Updated words equal to deep copy weights. So updated weights is originally the deep copy of these given weights, but now I'm actually updating it because I have the gradient and I have the required calculations. So updated. So what's our updated formula? Updated formula is this. Let me copy it from somewhere. So this is our formula that I'm going to implement here, that updated weight is equal to original weight minus learning rate into gradient of loss with respect to weight. So I have the original weight, I have the LR weight given as part of the arguments to the original function here, that is the train function, and gradient I just calculated. So I have all the elements to update the weights. This is I coming from the outer loop where I'm enumerating the original weight matrix all together. And now I have to also get hold of the actual index, which will come from the elan loop. Here, remember, here I'm looping through the each layer with an nd.nd and np.nd enumerate. So this should give me the actual respective weights values that I'm talking about here in this part of the calculation. Plus equal to no, that will be minus equal to because original weights minus LR, right? LR into grad, and that should be the whole process of gradient descent for a single epoch. So let's return this value, return weights updated, and also return original loss for this epoch. Okay. And now I will actually make use of this training process on an experimental set of data set. I'll just be creating a superbly simple numpy array as my x weights, that is the actual input values from at the start of the network itself, and also a y value So let's do that. X equal to, I'm just creating a simple array of 1, 1. That's my input layer, as simple as that. And the y value is, again, I'm declaring the y values to be 0. Remember, it's a binary classification problem we discussed earlier. 0. So this is my initial. So this is my x is the input value in this function, and also the feed forward function. Y is the output value. This is the ground to the actual y value. And from these, and the weights we already discussed in another file. Let's bring this weight variable here in the same file so that we can run all together. So these are my weights. So I already have the inputs, outputs, weights, and the second train function also needs an error, and that will be default 0.01. So now what I will do is I run the train weights function, that is train weights gradient descent, this function for 100 epochs, and for each epoch I take the loss for that epoch and append to an array. And okay, so let's declare a losses, LOSSES. This array will contain all my losses, original losses from each running through the each epoch while running the train function. And yeah, just remember now, this train weights returns me the updated weights and the original loss, and this losses array will have all the original loss for each epoch append to it. Let's do that so that it becomes clear. For epoch in range 100, w loss, this w is actually w updated, loss GNL equal to, let's give it a slightly different name, loss original. Yes, train weights gradient descent, and it will take my x, which is my input, and then output, which is my y, and weights, which is my we, this particular variable weights, and the final one is learning rate 0.01. And then I'm just adding these loss value to the losses variable, LOSSES, and loss for G. So it's simple. This train weight gradient descent function will run for 100 epochs, and for each epoch, it will give me as its return value the updated W and the original loss for that particular epoch. So what I'm doing is I'm just adding these all the losses to an array. And why I'm creating this array, so that now I'll be plotting this array, and I will show that the losses goes on reducing with when the number of epochs goes ahead. That is, for the initial epochs the losses are high, then with each epoch we improve our losses, that is, we reduce our losses more and more. So it will be a reducing graph plot. So let's plot that. ELT.plot losses and ELT.get loss over increasing loss over epochs. Now this is a .py file, so I have to create a Jupyter notebook and then I will run it through this whole .py file with a Jupyter notebook. 1 second. So now I have created this empty Jupyter notebook, and in here I'll be running or executing these external Python file where all my codes are, this file. This .py file to run here in this Jupyter notebook, I have to make use of the magic notation of Python. You can check out their documentation. One second. Yes, this is a documentation of these percentage run command in Python. It runs a named file inside IPython as a program, and it takes few parameters like in, I. The I argument makes runs the file IPython's namespace instead of an empty one. This is useful if you're experimenting with code written in a text editor, which depends on variables defined interactively. So I'm going to use this one. Okay. My file name is neural network from scratch.py. Yes, let's run it. Oops, I'm getting a straight line, horizontal line as my loss over epochs. So these are on the horizontal axis, that's my x-axis is my epochs, 0 to 100, and these are my loss. But obviously, this is a wrong one, so I must have made some mistake. The loss is not getting updated. So most probably the reason is why the weights are not getting updated. Let's quickly take a look at my code. My final, when I'm running the epochs, from the train weights gradient descent, I'm outputting updated weight and loss original. And oh yes, I found it here. So the mistake was that in this function I was passing the same input weights, but that should not be the case. And that's why, because my weights are not changing, this is a original weight that was passed to the initial epoch to the network, and I'm passing it again and again through these epochs, and that's why my loss is not getting updated. So I have to change it to w updated, and now it should work. Yes, so now we can see that as the epochs are increasing, the way the loss is continuously getting decreased. So it's a beautiful graph, exactly the way that I wanted it to be plotted. And we can see that after like 80 to 85 epochs, there's no further reduction in losses. So yeah, so that was about this entire video. Thank you very much for watching, and if you think that it's helpful, you can press the like button, or also think of subscribing my channel. Thank you very much.